Hello everyone, and welcome to today's presentation. I'm excited to have you here as we explore the fascinating topic of binary search trees. This is part of our course, 23CS1302, Data Structures. My name is S. Jagadiswari, and I'll be guiding you through this session. In this presentation, we'll cover the fundamental concepts of binary search trees, how they work, and their applications. So let's get started and dive into the world of data structures. A binary search tree, or BSD, is a special kind of binary tree that has an ordered structure. What that means is, each node in the tree has a key, and the placement of those nodes follows a specific pattern. On the left side, you'll find values that are less than the parent node's key, and on the right side, values that are greater than that key. This ordering makes BSDs incredibly useful because it allows us to perform operations like searching, inserting, or deleting data efficiently. In fact, their structure is what makes them so popular in applications where quick data retrieval is essential. So, understanding how BSDs are organized is key to leveraging their full potential in computer science. Let's take a closer look at the key characteristics of a binary search tree, or BSD. First, each node in a BSD has at most 2 children, which keeps the structure simple and manageable. The next point is about the ordering. The left child is always less than the parent, and the right child is always greater than the parent. This property is fundamental because it allows us to efficiently search for values. Also, it's important to note that duplicate nodes are not allowed in a BSD, which helps maintain the integrity of the structure. When we perform an in-order traversal, it produces a sorted output, which is incredibly useful for many applications like sorting or searching. Lastly, BSDs are particularly efficient for dynamic data sets, meaning they handle insertions and deletions well, making them adaptable as your data changes. These characteristics make BSDs a powerful tool in our data structures toolkit. Now let's talk about traversal, which is a key operation in binary search trees. Traversal means visiting all the nodes in a specific order. There are 3 main types: in-order, pre-order, and post-order. Each serves a different purpose and follows a unique pattern. In-order traversal visits nodes in ascending order, which is especially useful for retrieving sorted data. Pre-order is often used for copying the tree or creating a prefix expression, while post-order is handy for deleting nodes or evaluating expressions. These traversal methods are essential because they help us access and process every node in the tree systematically, connecting back to the overall theme of how BSD operations allow us to manage data efficiently. Let's walk through the process of inserting a new value into a binary search tree. First, we compare the value we want to insert with the value at the root. If the new value is smaller, we move to the left subtree. If it's larger, we go to the right subtree. We continue this comparison at each node until we find the correct spot. Once we reach an appropriate leaf node where there's no further child in the direction we're heading, we insert the new value there. This step-by-step process ensures that the properties of the binary search tree are maintained, making searches efficient and straightforward. Let's walk through the process of searching in a binary search tree. First, we compare the key we're looking for with the root node. If they are equal, then we've found our element. If the key is smaller, we move to the left subtree and continue the search there. If the key is greater, we go to the right subtree. This process repeats until we find the element or reach a leaf node. One of the key advantages of this approach is its efficiency. On average, the time complexity is O log n, which means it scales well even with large datasets. This is what makes binary search trees so powerful for search operations. They allow us to quickly locate elements by systematically narrowing down the search space. All right, let's talk about the 3 cases we encounter when deleting a node in a binary search tree. First, if the node has no children, it's the simplest case. We just remove it directly. No complications there. Next, if the node has only 1 child, we replace that node with its child, effectively bypassing the node and maintaining the tree's structure. And finally, if the node has 2 children, things get a bit more interesting. In that scenario, we replace the node with its in-order successor or predecessor, which helps preserve the binary search tree properties. These cases are fundamental to understanding how deletion works in a BSD and ensuring the tree remains properly ordered after changes. All right, let's talk about the different traversal techniques. First up, in-order traversal, which follows the left, root, right sequence. This method is particularly useful because it gives us the nodes in sorted order, making it ideal for tasks that require sorted data. Next, we have pre-order traversal, which visits the root first, then the left, and finally the right. This approach is especially handy when we need to create copies of a tree, as it preserves the structure in a way that makes cloning straightforward. Lastly, there's post-order traversal, where we visit the left and right subtrees before the root. This technique is very useful for scenarios like deleting a tree, because it ensures we delete child nodes before their parent. Understanding these traversal methods is key, because they each serve different purposes and help us manipulate trees efficiently in various contexts. Now, let's take a closer look at some practical applications of binary search trees. First, they play a crucial role in database indexing and search operations. By organizing data efficiently, BSDs enable quick retrieval, which is essential for managing large datasets. Next, you'll find symbol tables in compilers heavily rely on BSDs. These tables help in storing and retrieving variable names and their attributes swiftly during code compilation. BSDs are also fundamental in file systems where fast lookup is necessary. They allow the system to quickly locate files or directories, improving overall performance and user experience. Sorting algorithms and dynamic set operations often utilize BSDs too. They provide efficient ways to insert, delete, and find elements, which are core operations in many algorithms. Lastly, implementation of priority queues can be efficiently handled using specialized variants of BSDs, like heap structures, which are essentially balanced trees optimized for such tasks. In summary, these applications highlight how the properties of BSDs, such as efficient search, insertion, and deletion, are leveraged across various domains to optimize performance and functionality. Let's talk about the advantages first. One of the biggest benefits of these data structures, like binary search trees, is their efficiency in searching, inserting, and deleting data. Because they are organized in a way that allows quick access, these operations are typically faster compared to unsorted lists. Additionally, they maintain their data in sorted order, which makes tasks like finding the minimum or maximum or doing in-order traversals much more straightforward. Now, moving on to the disadvantages. A key point to remember is that if a tree becomes unbalanced, say, it turns into a long chain rather than a balanced structure, its performance can suffer significantly. Operations that were once fast can slow down, approaching linear time in the worst case. This is why self-balancing binary search trees often require rotations to keep the structure balanced, ensuring that operations remain efficient. Connecting this to our overall theme, it's clear that while these structures offer great advantages in performance and order maintenance, their efficiency heavily depends on maintaining balance. That's why understanding these trade-offs is essential when choosing the right data structure for a particular application. So, to wrap things up, binary search trees are truly fundamental data structures when it comes to managing ordered data efficiently. They allow us to perform search and update operations quickly, which is essential in many applications. It's also important to note that there are variants like AVL and red-black trees, which are designed to address balancing issues. These variants help maintain optimal performance even as the data set grows, ensuring that operations stay efficient. Overall, understanding these trees and their variants is key to building robust and efficient algorithms and systems.